All right. Hey Tim. So,
Hey.
I'd like to know if you don't mind if I record this interview for the analytical scientist.
That's great.
Cool. Awesome. So, the article that we are doing is one on a perspective of scientists in their pursuit for curiosity, their personal curiosity, and their passions, and how they've managed to fulfill them in some means, and just their perspective on how you can help mature scientists when it comes to the topic of curiosity. So I have a set of questions that I'll be asking. If you could just be honest with your perspective, and I also understand if you can't answer some things.
Great.
Cool.
I will. Thank you.
Awesome. So I'll also ask for examples, if you could give personal examples.
Okay.
Cool.
It might be harder to dig through that. But
So, what is curiosity in your opinion? What would you define it as?
being pulled into something that you weren't necessarily aware of, and then asking a question about it that takes you down a different way. So essentially just making the science real and enabling the science to sort of speak to you.
Cool.
I mean, that's sort of where when I look at information that comes out, I just ask questions of why, when you see something weird too, why does it look like that? And it just sort of makes you curious as to why doesn't that one behave like all the others?
Yeah. So can you give an example of where you've either saw data or instrumentation that you've developed that was really bizarre or that you wanted to correct for, that you just pursued?
Bizarre. I can't think of anything bizarre, but something that was intriguing me. Let's see if I can find one. So one that I guess was interesting was the inkjet printer.
Yeah. That
worked with Dodge Beluga on, and we sort of asked the question. Well, it was him who asked it first, and then we sort of got together and asked, well, could we just use a simple inkjet printer to make this matrix process work easier, because it's a pain in the butt to. Probably don't want to quote that one, but it's easy. It's not easy to cook tissue and something and make it simple. And then we took an inkjet printer and played with it, and it worked pretty well. I was surprised, but it took a simple question in terms of not necessarily a bizarre question, but a simple question that says, how can we make this better?
Yeah.
And then thinking about what we use on a normal basis to see how can we make it cheap as well and better. And so that was one thing that was pretty interesting. And I guess one thing that was sort of curious in terms of discovery was when I was working on lipid identification from tissue, in terms of trying just to understand really what they did, and in the process of just methodically going through each one, you sort of got to pick out the patterns that you sort of see that some lipids show the same thing all the time.
Yeah.
And then that then allowed you to sort of dig down and really sort of categorize things in a simple way from simple experiments that sort of just started with what is that compound, and how do I figure out what it is.
Okay. So then, if we go back to curiosity, my follow-up question to that was do you think it's important, and to what degree? Do you think curiosity is important as a scientist?
I think as a scientist, you're starved without it.
You're starved without curiosity.
Yeah, I mean, I think that's sort of why you're science. I think sometimes you're a scientist because you ask a question that some people don't ask. You just say, well, why does that work the way it does? But then you have to figure out how to answer the question.
Yeah, that's such a bold statement, though. Starved without curiosity.
Yeah, well, I think that. I think it is. I mean, I think because I have in my personal experience was coming from a lab where you sort of had total creative license.
Yeah.
And then starting a lab that was sort of more rigid, because you had to had to have techniques available that were not necessarily in building, but that you could answer the question quickly, but not necessarily innovatively.
Yeah.
And sort of transitioning from like super innovation to running a sort of more routine lab was a struggle until I figured out how to find
the two.
Time to balance the curiosity aspects of science.
Okay, I'm gonna revisit that a little bit later. But I do want to ask you about your undergrad experience.
Yeah.
How did that shape you as a scientist when it comes to like pursuing curiosity? What did your undergraduate PI like do to cultivate that kind of environment?
He basically gave me an opportunity in a project and the trust to be able to go and run an instrument by myself.
Yeah.
And collect and then develop a project on my own. And it was Maldi,
Mm-hmm.
working with Maldi, and so it was learning sort of an exquisite. To me, I thought it was a pretty exquisite technique because you're using so little material
Mm-hmm.
to get so much information from. And at the time, I sort of didn't really know how important that was because I had no idea that Maldi was going to win the Nobel Prize. At that time,
oh yeah, that's true, right?
It was in 98, 96 to 97. That was that time frame. Nobel
And then
Prize
2
was
years
in
later.
2004.
Was it 2004?
I think
Okay.
it was 2004.
Yeah.
So I knew the technique was amazing to
Mm-hmm.
me as an undergrad, and so it was a unique opportunity to have a PI who was willing to bring an undergrad in his lab, and then willing to let the undergrads sort of be a part of the research group. And I did have another graduate student who was a PI mentor. He sort of was more of the same kind of thing, is give you the tools to be able to do the work rather than sort of look over your back. And I think that was a unique opportunity to have both a PI and a graduate student who was willing to sort of mentor you, but maybe more mentor you on the aspects of this is just be a scientist. And once you know that you can't damage the instruments, which can happen with mass spec, then you can trust them to sort of just go and do stuff. So
Okay. And then what level of scientist do you think curiosity is kind of required for? Is it for a specific type of scientist? Is it something that all scientists should pursue?
Yeah, I would think that sometimes it depends on the job you have.
Is it a maturity aspect or is it the job?
Well, I think curiosity has to have the tools necessary to answer the question, because you can be curious and not be able to know what the answer is, and so that sort of, to me, I think that makes you're not able to solve the question at hand, and that can be frustrating, and so you can leave it. You can leave curiosity because of that. So I think at some point you have to have the training to be able to design an experiment to be able to solve that question without having to get frustrated that you can't ever get to the answer. So I think curiosity is important at all levels, but I think you need to have the right tools to be able to design something around it. To make sense of it.
So have you ever experienced the frustration where you've just left a project because there wasn't a tool, or like you felt so frustrated with the situation, like it defeated your curiosity and you couldn't find a way back to that question?
I haven't had one that we haven't just let go, but we've had definitely problems along the way in terms of either not having enough money to be able to go and get the question, and so having to sort of table the idea until you get money to be able to get the materials you need to do that, and that can be frustrating. So sort of an example now was trying to sort of take what we do now with imaging and make imaging more improve the art of imaging, and it's hard because that requires a big investment to do that.
Yeah.
Or the right collaboration. So I think some projects you just have to table until you know how you can either fund them or how you can find someone to collaborate with that would help take it to the next steps.
So have you found like collaborations the most beneficial way to, navigate around funding, or is it just your passion, like you keep applying for these grants?
It's both. So making sure that you don't get frustrated when someone says no, because sometimes people say no because they either don't understand or you haven't described it well enough.
Yeah.
And or it's a bad idea, right? Sometimes they could be bad ideas. You don't know until you try it sometimes. Like airbrush, when I was using airbrushing to spray into the ion source, that was interesting, because I wanted to create non-ion clusters that weren't ionized by electric current, to see if you could create a different way to do it. But then that goes back to the old days of thermospray and things like that.
How did you come up with that idea?
The airbrushing?
Yeah.
Because we had it.
And it was just available, and it was a means
to test to see.
Yeah.
Well, I was worried about source fragmentation.
This is like a real passion of yours, source fragmentation. Yeah, like it's a frustration that has led to like a passion to where you're constantly trying to solve the question of how do we eliminate source fragmentation.
Yeah, so I noticed that during the electric current can impart too much energy, and that causes fragmentation.
Yeah.
So airbrushing doesn't have any electricity, but it still produces fine droplets.
Yeah.
And I thought that could be a unique way to do that, to make it so you can do it, but so far it hasn't worked.
But you haven't given up on it, right?
I think that's one of the danger parts too, is that sometimes you don't know when to give up. And I think sometimes having someone that you talking about the science and having someone who's another scientist say, well, I don't think that here's maybe an answer to what you want, and it might not be what you want, but having someone else tell you sort of that you're just not going down the right way.
Yeah.
I think so we asked about collaboration. I think it's important to find a collaborator for certain projects, so that you're not just thinking your own, like you're not just using everything that you know, because sometimes another person comes in and says something that just changes the whole process and makes it so that you understand that what your original thought wasn't right.
Yeah.
So that's okay.
It is. It's challenging though, yeah, right?
It is. It's hard to, and it's hard to sort of share your science with other people, because there's
very much so.
There's worry that other people might, you might think it's stupid, or you might think that, or take it,
yeah,
one or the other, if you don't have a good collaboration. So in terms of being able to do things, I found having good collaborators enables you to sort of get extra money to sort of do it, and then bounce ideas off each other. So
yeah, that's interesting. I always think, when I think about collaborations, I think of the buckyball experiment and how these three guys, they were friends, like they had experiments together and they had enough trust and confidence in each other to where they could come to one another with this idea and move forward to something that, has changed kind of science.
Completely.
Yeah, so, but it's having, I guess, a trust with the people you can share your scientific ideas with.
Yeah.
So, yeah.
And then they'll make sure that you're still all included in the end.
Yeah. Yeah. So, I guess since you're a mentor now and you're on the verge to being tenured, how does curiosity, how important do you feel like it is to your students?
I'd say it's probably one of the most important things as a student to have, because you have to train. You can get so frustrated when things don't work right that you have to be able to answer questions and get out of the rut of, because research takes a long time.
Yeah.
I mean, it can be hard. Some projects, rarely does a project start and it's finished very easily. So along the way, I think one thing curiosity does is it sort of molds you into thinking creatively through problems, whether it's just being curious about a new question or curious about why your thing's not working, or trying to just talk about it. I think curiosity helps you relax as a scientist in some ways.
Really?
I think it can, because I think ideas sort of give you that. When you have a new idea and you like it, it sort of gives you some. I don't have any data for this, but I'm quite certain it probably changes a little bit of your brain chemistry to give you some more of an upbeat process in terms of how you make something happen. So I think in terms of doing things, I think having exercises for students to do curiosity thinking, even if you don't do it, even if you just say, here's an exercise in terms of here's an idea, let's talk about what creative ways to solve this, and then maybe you just leave it at that for a while.
Have you done that?
We've done it once. in a group meeting, yeah.
Oh, cool.
We talked about the problems first associated with doing metabolomics, and then we talked about ways in which you could solve each one of those problems, and then go through it. I actually got that from somebody else. A scientist had, when I was not in school, in between school and undergrad and graduate school, I worked doing in film coatings, and I had a boss who came in who did that. He would ask, basically, if you were in a room, he would ask everyone had to come up with an idea before you left the room. And it doesn't have to be good. Just come up with an idea for whatever idea, for whatever basic concept it was. And I think that was in general a good idea, because it helped people sort of forget about how hard it could be sometimes to do things. And that company was tough, because I think you were trying to do something that was really hard, and so you needed sort of a boss who was able to find ways to keep you from getting in a rut.
Gotcha.
And engaged in the actual science of discovery. So,
how do you nurture that? Like, how do you feel like you do that for whether it be for yourself, for students, for people you interact with? How do you nurture, and nurture might not be maybe too soft of a word, but like, how do you continue to aid others around you?
One, asking questions.
Yeah.
And two, being focused when you're interacting with people. So trying to remove the distraction sometimes, so that you actually hear and see what's going on in the research.
Yeah.
Seeing and listening to someone's talk. I think a student giving a talk is a really good exercise in curiosity, because going through and organizing your research in a way helps you sort of see the different parts of that research, and where there's gaps in it, but also maybe where someone else thinks something's really cool in it. And I think that then has you sit back and you look at it in a different way, because you didn't see that before, or you didn't understand it. So I remember many times in giving a talk and someone asking a question, like, well, I don't know about that, let me go find out. Because I think when someone asks a scientist a question, you have to answer the question. I think you have a different way of interaction. And I think questions in science are important. So I think doing that, giving talks to other scientists in a sort of relaxed environment, helps you sort of look at things differently.
Right.
I'm also married to an artist, so I see what artists do, and they have a different way to visualize, to be creative, and just what they do, which is you draw all the time, or you come up with different ideas. As a scientist, you can't draw all the time, but as a scientist, you can look at data all the time, and you can read other people's manuscripts all the time to sort of figure out what other people might be working on.
And what's missing in that?
Or what's missing, or what could be added, or what might be important. So that's what when I first got into doing imaging was I had a collaborator who was submitting a grant, and we wanted to know, well, what could we actually look for in the tissue that might be different if we were going to do imaging mass spec. So I spent the whole weekend in the library. Because at the time, it wasn't as digital as it is now, pulling papers and reading papers and really trying to figure out, basically starting with his concept of nerve damage, and then going down to the small molecules, because that's all we could measure, to see, well, what kind of molecules could we measure that might be changing as a result of damaging nerves and regrowing nerves. And so, but I had to spend a whole weekend because I had no idea what I was doing. And then we came up with an idea. It got funded.
So it got funded. It's like, it's the idea, that's the dream. But what happens with your failures and just facing the sense of defeat with a research project? And then if you could give an example, if you had.
That one is a perfect example, because we wanted to look for certain compounds that were there, and we tried every which way to do it. We could never see them.
This is the
DCA,
okay.
Looking at dichloroacetate, looking at other very small molecules in tissue, because ideally to see where the distribution of them is, and then see if they're interacting with other molecules, but we could never see them could never look for them. We could look for them, but we could never figure out if they were there, if we could detect them. It was just too difficult, so we could never do that. And the frustration of that was trying to tell the collaborator that we can't do it.
Yeah.
Because it was something that the experiment just doesn't work, and then trying to figure out.
This was by Maldi?
By Maldi,
okay.
Right. And then trying to figure out how to not salvage it, but then trying to sort of turn it to say, well, you don't necessarily need to look at that. We have to, the other aspects are important too. So that's where the lipids came in. Trying to understand how the lipids were being altered as a result of the drug, even if you couldn't see the drug. And so that sort of led down that pathway, that you didn't have to look for this. Because some things as a scientist, at some point, you do have to say, I can't do that right now.
Yeah.
And I've exhausted all of the things I know how to do to be able to do that.
But you just redirected the question. You asked a different question that still had implications of what you were trying to answer in the initial one.
Right. Yes.
It's interesting. That's good. I mean, it's good. That's a great way to think about it. And a great way of not burning out and not feeling defeated, because it seems like it, I mean, especially when it comes to mass spec and how we analyze samples, people want a specific answer sometimes, and
Always.
So not being able to deliver that specific answer, it's cool that you can redirect the question and being mindful of that. So
yeah, and I mean, I think that's the danger of analytical chemistry too, is that you can, some people believe it's a definitive answer all the time, and you can't always get the right answer or the correct answer sometimes.
What they deem correct, right?
Correct, yes. So you have to sort of think about it outside of the window that you're going down.
And then my last question is about like your research. I know you're a clinical mass spec scientist, but have you ever, I guess, is research without a direct application feasible? And then do you think about research that doesn't have like direct applications? So something that is very fundamental from like a physics standpoint. How do you pursue those projects?
It gets much harder the more I'm down in an applied field, because you have to, you don't necessarily have the freedom to sort of answer a question that you can't get funded right away. Mm-hmm. And I think because it's such an applied area, we have to sort of do it with applied technology. But the way I've been trying to balance it is to make sure that the students that are involved do more than just looking at the applied questions, and think about the fundamentals that might be there and how we could solve those. So I think that's a key part to me. But then also thinking about harder questions. One of them that I've been trying to do for a long time is looking at wide isolation MSMS events to see how that affects overall MSMS efficiencies as well as doing quantitation, which is really more of a fundamental question in terms of what's going on inside the mass spec when you put two ions together, but then you want to quantify both of them, or one of them, and use the other one as a reference. But finding the time to spend on that sometimes is a balance. So I think it's up to me to devote the time to it. Yeah. And to say to schedule it in, to say I think it's important enough to do this, and it's interesting enough to me. And then balancing it with what we already do. So. Yeah. But I mean, and also because I'm in clinical and applied to patients, we sort of want to make sure that the question we answer is reliable, and the method we develop is reliable enough that you can measure what's in a patient and measure that patient's response is somehow related to another disease. Because the last thing you want to do is give someone a result that's wrong, and then tell them something as a result of that. So I think that the sort of, when you put that perspective on, you sort of you might take longer to take a fundamental question to the patient, or it may never go there. But, so
that's tough.
That's
I mean that's clinical research though.
It is. I mean, it's designed to be more applied. So you sort of have to the good thing about it is that you can answer fundamental questions, or so the unique thing about it is that you get in a research study that's approved, you get patient samples that you can then use to answer fundamental questions like, okay, I can use a solid technique and I can answer the question now, but I can save these samples, and I can also, as long as I'm allowed to save the samples, I can save those samples, and I can then ask other questions with those samples, using the same, the same ideas. Like, you know, can I measure metabolites using this way, or can I measure metabolites this way in that same sample, and can I get the same answer from them? And then I can go back and say, well, why is this working better than this one? And that's really more for me, because I've already given the results that might affect that other research study. So that's sort of what I look at as a unique opportunity.
Interesting. And one more question. This is a fun question. If you could think back, whether it be to high school, your childhood, or undergrad, a point in time where you can maybe pinpoint curiosity, like where you became just curious about, whether it could be about anything, honestly, but if you could pinpoint something where that kind of sparked your sense of curiosity. Fun fact about Tim. I mean, whatever it may be, it doesn't have to be a fun fact.
I mean, I think the thing I got curious about chemistry in general was definitely when I transitioned in undergrad, transitioning from organic chemistry for non-majors to organic chemistry for majors, because I liked chemistry and I liked it when it was organic, because I could visualize the chemical in my head, I could see the structure, and I thought so that was something that was sort of curious in terms of how far could I go to see other things, how if I could do this. But then I got hit with organic chemistry for majors, and it was really hard. So I had to change sort of what I was doing in terms of I had to spend more time devoted to doing chemistry and learning more about it. And I just sort of in that process I found that I really liked doing it, and I really liked the curiosity of what happens on the molecular level.
Yeah.
So I just liked, you know, that this molecule putting together with this molecule creates another one, right? And then, but these don't. And then looking at how to measure them was the next step. Was then led to looking at MALDI, time of flight, and trying to figure out, well, how can we measure what those look like? And that was then taking small amounts of sample, but then looking at even something smaller. Yeah. And so I think that the ever sort of taking the macroscopic view, and I got really curious about the macroscopic down to the microscopic, looking at, seeing sugar, but then really knowing what it's made of, and seeing the chemical, rather than seeing table sugar, I see the chemical bonds. And it's kind of weird, but I visualize the sugar, glucose, and sucrose in the, glucose and fructose in there. I don't visualize sugar, and so it's kind of, that was when I started being curious.
Cool.
Yeah.
Awesome. Well, thanks.
Yeah.
Thanks, Tim.
No problem.